Speaker of the morning is going to be Ilan Lobel, who will be my future colleague at NYU Stern. So he graduated from MIT, and his research interests are in pricing, learning, markets, networks, and mechanism design, and he'll be talking to us about some cool work on sort of contextual inverse optimization. Oh, the lights. Cool, take it away.
Thank you very much, Jackie. Thank you, everybody. So let me tell you what the paper is about, and then I'll explain what these words mean here. There's a lot of words in this title. So here in this data-driven decision process framework, our typical setup is something like a contextual bandit, right? Where we get some context, we choose an action, and then we get a reward. But there are many settings of interest where you can't actually observe rewards. And this is going to be our theme here. And in settings where you can't observe rewards, and I'll give you some examples in a second, what other feedback might you be able to use to learn from? And what we're going to study here are settings where instead of learning the reward, you learn after the fact what you should have done. So this is what we're going to call contextual inverse optimization. And in the next slide, it's going to be clear what's the mapping between the terminology and the problem. But let me give you some applications. So one application in economics and like choice modeling is learning from revealed preferences. So I see people observing bundles of goods, and they have prices, and they choose to buy some subsets of those goods. I never observe their rewards, right? I don't know how much utility they got out of it, but I know what they bought. So I can use the fact that they bought bundles of goods to try to make inference about what optimization problem they were solving, what utility function they had. In robotics, people use this stuff a lot. It's often called inverse reinforcement learning there, where it's very hard to give a utility function to a robot or an autonomous vehicle, but you can tell an autonomous vehicle, you made the right thing here, you should have done this. So again, so the idea here is I'm never gonna observe exactly the utility function that I need, but I have sort of like, if I chose an arm, I know like, no, I picked the wrong arm, I should have picked this arm. And you can think of applying this for medicine too, like for many applications in medicine, you don't really know if a medicine worked, it didn't work, right? The doctor prescribed something, but you can tell a robot, no, you prescribed the wrong thing, you should have prescribed this instead. And how we're going to think about this mathematically. So in every period, so we're going to consider two versions, an offline and online version, but you can think that in every period, you want to solve a problem of this kind. And here is why the name contextual, because every period you have a set of actions and a context function. And the problem is we don't know a cost. So there's some cost vector I don't know that I need to learn. But I do observe the set of actions, the contextual function, and an optimal action after the period. After I make an action, I observe some optimal solution of this problem. So it's inverse optimization because I observe a solution of an optimization, and then I want to learn the cost vector, and it's contextual because I have these f functions. And just to keep a problem in mind, you can think of the learning from revealed preferences example like this. Like every period, you have a bundle of goods with prices. So there's a bundle of goods with prices, and you have a budget. And let's say there's and I want to know the values of the features of the goods. And this matrix V will map from features to products. And then I see which products you buy, and I want to learn how much you value different features. Or another example is, I want to understand how Harvard chooses its class. I have no idea how what the Harvard committee is optimizing, but I want to try to understand what it is that they're optimizing for. So I know that they have a budget of people, and they care about SAT scores, athletic ability, and a bunch of other features. And I might be able to observe who they accepted and who they rejected. And from that, I want to sort of like try to make some inference about what is the problem that they were trying to solve. And quickly, the literature on inverse optimization dates back to this paper from 20 years ago by Ahuja and Orlin, where given an optimal action, you want to estimate a cost vector. There's a much more modern treatment, for example, by Timothy Chan out of the University of Toronto. In terms of closest stuff to us, there's this paper by Esfahani et al., which is a pretty celebrated paper. It won the the Lanchester Prize, which is closest to our offline model. And the closest paper to ours is actually going to be this Barman, Pokut, and Schneider ICML paper, which is going to be closest to our online model. And what they do is that they do a reduction to gradient descent, and they propose an algorithm for this. There's also a literature on contextual pricing and contextual search. The Hara, where's Hara? Over there. Hara is going to be presenting about this stuff later on. And I'm going to argue, we're going to leverage some of the techniques from this literature, but I'm going to argue that the problem's actually quite different because you have a lot less knowledge about the problem than here. And there's also a big literature in CS on inverse reinforcement learning, structured predictions. I'm not going to stop you. And I forgot to mention that the actual brain power behind this problem, behind this paper is not me, it's Yuri over there. Yuri, can you say hi to everybody? Thank you. So Yuri is a PhD student at Columbia. He's the person who should get the tough questions, as Vivek said. And what is it that we do here? What are our main results? For the offline model, we're going to do some geometry here, and I'm going to propose some geometric notion of how informative a data set is, and then use this notion to characterize and minimax regret. And then for the online setting, the state-of-the-art result is this order square root t regret from Barman, which assumes linear context functions. So we're going to generalize to any Lipschitz context functions, and we're going to get logarithmic regret. So we have an exponential gain here from square root t to log t regret, but we pay in terms that the geometry is going to give us some dimension coefficients in the regret. So let's get started with the offline setting. The offline setting, I'm given a bunch of data, and I want to know how good can I make a future prediction based on this data. So I'm given feasible actions for a bunch of observations, the context function for each problem, and what is an optimal action in each of these problems. And all of these satisfy this equation as I described before. And given this, I can use, I'm going to use the letter D to describe my data. And let's use C0 to define my initial cost, my initial set of possible costs. And let's normalize this to be on a sphere. Because I'm never going to observe rewards, right? So if the costs double, I'm not going to observe anything different, right? So you can assume that this lives on the surface of a sphere. And given the set of initial costs and my data set, this is the set of feasible costs that I might have given the data observed. Clear? So this is everything that I can know based on my data. A policy is a mapping from my data set, and the next problem I'm going to face to what I should choose in that problem. Yes,
there is no noise, or there is some?
There is no noise in this model. So this literature, the Barman paper, our paper doesn't have noise. We're working on a version now for a noisy version, but for today, there's not going to be any noise. You observe exact actions, which is kind of like the most classical version of inverse optimization. But obviously, to make this practical, you got to figure out how to add noise here. But today, there's no noise in this presentation. And you can ask Hara, she's really good at adding noise to things, and Todoris. They have, because I've done other work in contextual pricing and search, and they've added several versions of noise in those papers in their own work. Our regret is going to be very natural, right? How much our cost is minus how much would be if we knew C star, how much the optimal value is. And this is going to be an adversarial model, so I'm not going to make any stochastic assumptions about how the data is generated. So I want to know the worst case. If nature throws me the worst problem and the worst cost here, how much is my regret? So WCR stands for worst case regret. And this is pretty general. This is the set of all measurable sets within a bounded set, and this is the set of all Lipschitz continuous functions. So in an adversarial setting, I can't do the usual thing that you do in learning, which is say, as n grows, how much better is my data? And why can't I do that? Because nature can be mean to me, and nature can send me the same problem over and over. So there's no notion that as n grows, I can do better, right? So only if nature gives me better data, I can know better. So it's possible that I can learn nothing. So I need some sort of notion that if the data is informative, I can do well. And I'm going to have to define what does it mean for the data to be informative. And here's where we're going to use some high dimensional geometry here to try to think about what is the notion of an informative data set? So in this whole literature, everybody works with a set of proxy policies. And what is a proxy policy? The set of actions is too unwieldy to work with because the action set keeps jumping around from problem to problem. So what you work on, the typical approach in this literature, and then we're going to follow this too, is you guess a cost vector. I'm going to say, I think this is the true cost vector. And this is what we call the proxy cost vector. And based on this, my guess of what the cost vector is, I'm going to choose an optimal action. And given, if I have a proxy cost and a true cost, then I can define some sort of like worst case loss here, right? What is the worst case loss? The worst case loss is like, if my cost is this and the true cost is this, how bad can I do? And it's not too hard to argue that if I optimize, if I think about what is the worst case policy, I can think about it in the sense, I can transform this into this minimax problem over proxy costs. So there's a restriction here that I'm restricting myself to proxy policies, but then I can turn this into a minimax policy on these vectors. And this is going to be nice because I can bound this loss based on the geometry of the problem. That is, theta is the angle between the two vectors. So the loss is given by the sine of the angle between the two, if the angle is small enough. If the angle is big, 1 is the worst case, so I can't do anything. So if the two, so it's pretty intuitive, right? If I think the cost is this and the true cost is not too far away, my loss is not that bad. And it's intuitive, but it's actually hard. Actually, the way we prove this lemma is via semi-definite programming. And if you have questions about that, Yuri is the man. But so the technical work to prove this is harder than it looks based on the statement of the result. But I'm going to take this for granted, which is this notion like I can reduce that notion, that problem to a geometric problem. And remember, we've reduced first to a minimax problem over the loss. And now we're going to turn this into something about angles. So now what I care about is this sort of like minimax of the angle. So remember, there was a sign here, but I can take the sign out because I only care about the term where sine is monotone, right? I only care about this for small thetas where sine is monotone. So I can turn this into a minimax over angles between the true cost and the actual cost. And I'm going to define this notion here, this minimax, to be the uncertainty angle. And the minimizer, the see how the minimizer is, we call the uncertainty, the circumcenter. And it's pretty intuitive to understand what this means when you think of geometrically. So imagine you have a set of, so I said the costs live on the surface of a ball. So the set of costs, let's say it's here. So what I want to do is fit the smallest cone I can around the set, the smallest revolution cones, the smallest second order cone I can fit around the set. And the axis of this this cone is going to be my circumcenter, and the angle here is my uncertainty angle. So what is this notion here saying? That if I have a data set here, and if I can fit it within a small cone, I can do pretty well. If I have to fit it on a large cone, I'm going to do pretty badly. So the offline problem reduces to this geometry problem of angles, right? Can I sort of like, is there a small angle? Is there some vector that has a small angle to everything in there? Yes, Hara.
Would you like to comment a bit why angles instead of like some L2 norm? Difference between the two C hat and C star?
Why angle instead of an L2 norm? What?
Why is the angle so powerful?
What'd you say? Sorry, you said.
It's all in the unit ball. So
yeah, so it's within the. It's on the surface. It's on the surface of a ball.
Sorry, yes. Sorry.
So we're going to call the proxy policy where I choose my proxy cost the circumcenter policy. And naturally, from what I said, the optimal proxy policy is the circumcenter policy. So if I have an offline data, what I want to use is the circumcenter policy, just sort of like guess this, try to fit it inside a cone, pick the axis of the cone and guess that number. And this gives me my worst case regret. We wrote the theorem here in terms of proxy policies. We have a slightly more complicated statement in terms of general policies. I'm not going to present it here, but the result extends to general policies with some slight caveats. And now the uncertainty angle defines a regret, and this bound is non-trivial if and only if the set of costs live in a pointed cone. So that's the offline problem, what we can say about. Now I want to jump to the online problem, which I think is a more interesting and more challenging one here. So in the online problem, I'm going to have t periods. Every period I'm given a feasible action and a context function, and then I'm going to choose an action in this feasible set. And after the period, I observe what an optimal action would have been. And now I can repeat some of the same argument. My information set is now what the feasible set of actions, the context function, what nature did and what I did in each period, plus the problem I'm facing today. And I can create the set of, just like before, the set of vectors that is consistent with my purity information set. And a policy is a mapping from the information set, what I should do. And I care about regret, which is very naturally defined as like how much I'm losing minus how much nature is losing. And my objective is to minimize worst case regret. So nature, again, adversarial bandits kind of thing here. So when we try to look at this problem, our first approach is try to use the techniques from the previous work that we did in like contextual pricing, contextual search. But the first thing you start to realize is that actually you have very little control over the feedback. Because you have really no direct control over the feedback. Because look at the problem here. So this is your information set. And look what shows up in your information set, which is the feasible set, the context function, and the optimal action. But your own actions, the things you've chosen, don't show up here. And this is different than pricing, right? In pricing, you choose a price and you learn if the valuation is below or above the price. So you have much more control over the learning process in a pricing problem or in a search problem. Here you don't actually you don't control anyway this information set. So this implies that maybe you should ignore the dynamics and do something greedy. This statement is false, but I'm going to pretend it's true for a little bit, that something greedy is good. There is going to be a way to control the information set. It's very subtle, and it's part of how we get there. But for now, I'm going to pretend I want to do something greedy, because I'm taking this view. Oh, xpi doesn't show up here, so I'm going to ignore xpi and just do the greedy thing. And the greedy thing is circumcenter, right? So the offline optimal is the same thing I should do if my game ended today. I should just do the offline optimal thing, right? Use all previous history. So the offline is a key ingredient here. So I should do the circumcenter. Yeah.
Just to make sure. So what is the feedback that I see here?
You see this. You see what problems you've chosen. At the beginning of the period, you see which problem you should choose, you should solve. And at the end of the period, you see what you should have done.
So it's exogenous. I don't control at all the feedback.
Yeah, nature chooses this.
Nature chooses.
It looks exogenous, but I'm going to argue you actually have some control over it in a very roundabout way. So that's part of the interesting thing here in this work. But at this point, it should look exogenous. Yes, right there.
This should be stationary or function should be
It's not stationary. Adversarial. Nature can throw whatever it wants. It's a worst case model. I'm not making any probabilistic assumptions. So now I'm gonna, the next theorem says that the circumcenter policy fails miserably in this problem. And what do you mean by fails miserably? You get regret that is linear in T. So the greedy policy does not work. And how do we prove that this doesn't work? Which is nature can construct instances where you get every period lots of regret and you learn almost nothing. And I'm going to walk you through how this works, how nature can do this. But the instance looks kind of like this. So the set of feasible costs are here, or this blue set, and the circumcenter is going to be this vector here. So the circumcenter might be strange that it's on the boundary, but actually the circumcenter of the set is on the boundary. And this is going to play a key role in the story here. So how does nature mess you up in this model? Which is, suppose your set of feasible actions in period 1 is 0 or x1 is over here. And there's no context function. The context function is the identity function. Now, the proxy cost, I said, is over here. So you do the inner product between this, and that's negative. That's better than choosing 0. So you choose x1. You choose action x1. Nature, on the other hand, knows the true cost here. nature chooses 0 because there's a positive cost here. So nature is causing you to get quite a bit of regret here by choosing this cost. And the problem is nature gave you almost no information. So what is the feedback that you have here? You know that this was worse than choosing 0. So you know you can add a hyperplane here that is orthogonal to x1. But look at what you're cutting. You're cutting nothing out. You're cutting like this essentially at the circumcenter. So the problem is nature can give you a lot of regret and essentially cut almost nothing out of your set. So what control do we have? If that doesn't work, is this a doomed problem? And if it was, I wouldn't be here. So let's assume that you made a bad choice. So if you made a good choice, you don't get regret. I don't care. So let's say that you made a bad choice in a period. By the optimality of xt star, this inequality is true, which means I can add this to my constraint to my knowledge set. And I'm going to call this like the difference in actions here. So difference in actions in a product C star is negative. And we do have some control over this. And what is the control that we have over this? Because by the optimality of xt pi with respect to my proxy cost, I get that this inner product here is positive. So the difference in action inner product ct pi is positive. And if you come to think about this, what am I doing? I know that I'm adding a constraint of this kind. Difference in action C star is negative. And I know the difference in action ct pi is positive. And imagine that these were strict inequalities here. This would mean that nature needs to cut off the proxy cost at every period. Nature needs to throw away the proxy cost in each period. It's not exactly true that because these can be equality. So nature can throw the proxy cost at a boundary. So what this is saying is that whenever I choose a proxy cost, nature needs to cut through it, needs to throw my proxy cost at a boundary. So when we don't learn much is when the proxy cost is right on the boundary. So that was the problem here. The proxy cost was right on the boundary. So I do have an exploration-exploitation trade-off here, which is if I want to exploit, I want to choose a circumcenter, which might be on the boundary. If I want to explore, I want to choose a cost in the middle of the set, and middle defined by distance to the boundaries. And then I'm going to force nature to cut through it. So we call this inverse exploration because we don't really have control of information gain, but to cause regret, nature either needs to cut this guy or at least move it to the boundary. And we can choose we can choose a proxy cost that forces nature to pick one of them. Either nature gives us regret or nature gives us information. So it's a different way of learning than like in classical statistical learning, because the way your control is by forcing nature to choose one of them. Either nature causes regret or gives you information about where you should go. And the circumcenter actually is a trap that greedy policy fails because your knowledge setting evolves by incorporating half-space cuts. And you end up having this polyhedral thing. And when you have a polyhedral object, very easily the circumcenter ends up on the boundary. So you don't want to be working with polyhedral cones. So the technique that we do is we regularize a knowledge set. And we're going to replace these knowledge sets by superset that contain them. And in particular, we're going to use ellipsoidal cones to do this. And this is a technique we used in the other paper on contextual pricing. There was like ellipsoids, and here's ellipsoidal cones. But you can sort of like, you can work with these. And why are ellipsoidal cones nice? Because now if you think of my set as an ellipsoidal cone, then my axis, which is the point further away from all boundaries, is also my circumcenter. So I force nature to, I don't have that trade-off with these kinds of sets between explore and exploit. How am I doing on time? Okay, good. So the basic of the algorithm is you have an uncertainty set, which is an ellipsoidal cone. You choose a proxy cost based on it. Then you choose an action based on this proxy cost. And then you collect this feedback. And now we do something a little bit delicate here, which is you update this cone only if this difference in actions here is sufficiently informative in a new direction. So you're going to have two types of periods here. You have low regret periods when this is not very informative, I just take the regret. And when this is very informative, I get I update and I gain information. And why do we need to have these no regret periods? That's kind of the cost of using ellipsoids, because ellipsoids have a tendency to become ill-conditioned. So if I cut this thing and it starts shrinking this way, it starts becoming long in this direction. It's a known thing of the ellipsoid method. And if you sort of like say, I'm not going to do cuts in small directions, you can avoid this problem of ill-condition. And to make this work, we needed to adapt the ellipsoidal method to work on ellipsoidal cones. And I'm not going to go into the details here. It's not trivial, but it's all in the paper. And this gives me a regret that's d squared log t tangent of the initial uncertainty angle. So this technique works, but only if my initial uncertainty angle is small. Now the question is, can we relax this? And that's what we're going to do next. So if we start from like a non-pointed set, what happens here? So if I have like lots of dimensions, nature can play a game with me. And what is a game that nature can play? Nature can like ignore one of the dimensions. So let's say I have 3 dimensions. Nature only plays in these 2 dimensions. So it only gives me information in this dimension. So I never learn anything about the vertical dimension. So I never get a pointed set. But what can I do in this case here, where nature is sort of like playing this game with me and trying to avoid me from learning? Nature can't give me a regret in this based on this dimension if it never uses it. So what we do is we ignore unused dimensions. If nature decides not to use a dimension, we don't get regret from it. So what we're going to do is say, look, we're just going to work in the subspace where nature has given me information on. And this idea of projections is also present in the literature. So we sort of like we're combining these techniques from the literature. But we have to use it a little bit differently here. And we're going to keep track of the subspace. And what happens here? If I get some information that's close enough to the subspace, I'm going to ignore the orthogonal elements of this. And I'm going to do ellipsoidal cones in that period. I'm going to sort of like do that ellipsoidal cut. I have to be a little bit careful here because now I'm throwing away some information. So there's some error that I introduced to the process. So I need to robustify this process. And if you know the ellipsoid method, there's this technique called shallow cuts to make it more robust. Like you don't cut through the middle, but you cut just part of it off. So we can robustify the technique. But if nature gives me delta t that's far enough from here, I can update my subspace. And now I have 3 types of periods. These like periods where I get low regret. These periods where I update my information within my subspace. And I have these periods where I do this dimension update, where I move to a higher dimensional space that I'm keeping track of. And the challenge here is you want to do this dimension update only if your information set is sufficiently far away from this delta, because there's a trade-off here. Because you want to keep a gap. Because if you do an update and you have very little information on the dimension, you're not gonna get something that's very non-pointed in that dimension. But if you also do a big thing here and you don't do an update, then you have a lot of error in your local subspace update, in your local cone update. So there's a gap, there's a trade-off that we need to sort of like optimize between like saying how far this needs to be from the subspace for me to do an update, whether I want the subspace updates to be better or the cone updates to be better. So there's a ton of technical details here that obviously I'm not going to get through. But the high level message is this works. So this costs us some in dimensions, right? So the last algorithm was d squared log t times the tangent. Here I can get rid of the uncertainty set. So I can actually, this technique here, this more complicated version of the algorithm works for any initial knowledge set. And it's the first log regret for this class of problems here. So summary of online learning. So the technique that we did is that sort of like, first we started with offline learning. And I argued that you should build that cone around your uncertainties set. And your circumcenter policy was a greedy policy there. And this doesn't work because we also needed something to force nature to explore, right? Because if you do the circumcenter, you might end up on the boundary. And once you're in the boundary, you're trapped because nature can make sure you don't learn. And we can make this policy work by making a number of adaptations. We can replace the polyhedral sets, which are bad for learning, with ellipsoidal cones. And then we can adapt the ellipsoid method to work with ellipsoidal cones. And then we skip the knowledge sets and low regret periods to avoid these ellipsoidal cones from getting ill condition. And then we maintain the subspace where we maintain a subspace where the knowledge sets are pointed. And you combine this all, you get a log regret for this problem. So what are some takeaways from this problem here, which is there's this classical bandits, you always assume you observe rewards, but there's problems in practice where we're very interested, they're very interesting, like learning from review preferences, where you don't observe rewards, but you just, and the particular case that we want to explore here, that we're exploring this paper is learning from optimal actions. And it's sort of like this interface of OR and machine learning, this class of problems. And it gives rise to a novel family of algorithms. So there's like all sorts of like new things that we can do here to tackle these problems. And the way learning happens is very different than statistical learning. It's just called, in the literature, this is sometimes called imitation learning. And the way you drive exploration is by forcing nature to explore for you if you don't want to give you regret. And I saved a few minutes at the end to talk about a different paper because everybody here is talking about marketplace interference. So I decided I need to pitch my marketplace interference paper here too. Yes.
So your adversary is adaptive, right?
My adversary is adaptive.
So in many applications, you can think of slightly weaker adversaries, for example, non-adaptive.
Yeah.
Can we say anything?
Well, these don't apply, right? So I don't.
Yeah, for sure, but
Can you do better?
Yeah, much better.
I mean, the Esfahani paper is a stochastic version of this, and there you get these like instead of having these things that are like worst case, you have the C-var type constraint, and you can do really well there. So it's a different framework, but yeah. So I think in the spirit of like jumping from stochastic to there's a whole spectrum of from this worst case to fully stochastic. Yes, Doris.
Can we discuss it with the dependence on the MS? Like
Yeah, so
it's perhaps a gloss, for example, we don't need to look the dependent the forest.
so d to the 4, I'm pretty sure it's not optimal. So d to the 4, we lose 1d. So we lose 1d from going from just from the ellipsoid method, and we lose 2 more d's when the subspace updates. One of them is like you got to count the number of subspace, and another one comes from the pointedness of the sets when you do the updates. It's plausible that there is something here. I mean, even the log t is not obvious that it's optimal, right? So like the contextual search and pricing papers I did, we ended up at log t. But then other people like Renato and John Schneider, Renato Paislame, John Schneider, they did log t, right? And you're saying there's even a possibility of doing bounded like finite regret here. I'm not claiming any of this is optimal. What I'm claiming is the frontier was square root t, and we were able to push it to log t. I wouldn't be surprised if there's a log t, but if you look at the, you have to see how, I mean, I know you're aware of how much work it goes into like pushing from log t to log t. So it's perfectly plausible that there is a future paper that will push this further. That's a great question. There is no, I don't know any lower bounds on this problem, as in like how hard it is.
So is it possible that maybe picking a different type of center, although sacrificing a little bit in the offline exploitation might actually better behave in terms of hedging against?
Yeah. So there's one way that I think you can easily gain a D here is instead of doing the ellipsoidal things, you just choose, you keep a polyhedral set, and then you choose a vector that's kind of like far away from, that's kind of like somewhere an interpolation between the circumcenter and the point further away from all the boundaries. That's just a lot harder to keep track of because these polyhedral sets become really messy.
I'd actually do the same thing, like, and specifically I think with the Steiner, right? Like there's this whole literature of like.
Yeah, and that's how Pike-Lemmy and Schneider improved the other one.
Yeah.
Was using Steiner.
Yeah, so if I map this maybe to that setup, now what that would require is that like your quote unquote feasible region of points is convex at each point to get.
Yeah, I'm not assuming anything here.
Yeah, I know you're not.
Yeah, so it's one of the beauties here is that we're working with like a really adversarial setting, and the only thing we assume is that the context function is Lipschitz, but the feasible set of actions is arbitrary. It could be an integer programming problem. But I totally believe the claim that there are better algorithms for this problem than this. So great open questions.
I might have a simple question. I mean, in this problem setting, at every step you have the action set and you have the function and you observe the oracle best action later.
Yeah.
And that allows you to cut down the unit sphere a little bit at every step. I'm just confused about. I mean, that's the best you can do, and that's the most information you can get from all the history. So I'm just a bit confused about the non-trivial part of this problem setting.
What is non-trivial here?
Yeah, because at every step you can cut down the unit sphere a little bit, and I think that's.
So yeah, but the main idea, the main insight is, I think your question is a good one because it looks like greedy should work, and it doesn't. It fails pretty miserably. And the idea that, and I think the key insight that when we crack the problem is that you need to sort of like make sure that your point is somehow in the middle of the set, and that forces nature to cut through the set, and then you can learn. I think that's the sort of like the key insight that allowed us to get traction with this problem, was this idea that like if you need to somehow don't do something greedy, which looks like it works a priori, but it doesn't, right? So we did all these experiments, it wasn't working, and then we started like trying to figure out why. And I forgot to put here on the slides, but Yuri has done all the simulations. This works faster, better than OGD on some simulated data. Yeah.
I have a question about the model. So you have both the context function, which is known, and the set of actions, which is known.
Yeah.
Is this, could you model it as just like you have a set of, vectors that deal with dot product with the false vector, or is there something special?
Yeah. So the part of the new approach that we're doing with Yuri, the new stuff is doing a functional approach to this. It's possible that yes, there is other ways to formulate this that are potentially more powerful. Okay. So I'll give you that. Yeah. It's a great question. So now I have like 5 minutes, so let me teach you a different paper. Because everybody here is thinking about interference in marketplaces, and I feel like, hey, I have a paper on this too. So this paper is with Ido Bright, who is at Lyft, and Arthur Delarue, who was at Lyft, but he's now at Georgia Tech, was a postdoc at Lyft. And when we started working on this paper at the beginning of the year, all the papers were either there was Hannah's team that worked with Airbnb, Guido Imben's team that worked with Amazon, and they all work with these like choice-based marketplaces. And what am I calling choice-based marketplaces? These are marketplaces where interference is super hard to model, because if you do the thing that Vivek and Hannah were describing, where you treat half the people and then you suck up the houses, and that causes an interference on the other half, it's really hard to know how the control people are going to respond to that. But I was working with Lyft guys, and they're like, look, our marketplace is not like that at all. When you order a car on Lyft, or let's say we order deliveries on DoorDash or something, you press a button and say, hey, send me some food or send me a driver. And there's some optimization that is run to dispatch a car to you, or a driver to you, or deliver to you. So the main argument in our paper is it's a lot easier to do interference control here than here. It's actually quite distant. And in particular, the main result that we have is that if you're in a matching-based marketplace, like if your dispatch is, if the way interference happens is via a dispatch problem, for example. Because think about an Uber or Lyft case. You have the same interference, right? If treatments are to order more, you don't have as many cars, control is going to order less because they're going to have less availability, longer ETAs, you're going to have all these problems. So you have exactly the same issue of interference, but here in the setting, you know exactly what the interference looks like. And what do I mean you know exactly what the interference looks like? You're the experimenter, you're also Uber or Lyft. You know the linear program you use to dispatch people. So you can use the linear program to correct things. And the correction that we come up with is really simple. It's just do your analysis in the dual space instead of doing your analysis in primal space. Instead of adding like all treated minus all control, you take all, you look at your matching linear program, and then you look at like the shadow prices of all the treated minus the shadow price of all the controls. And we proved that this is actually the correct first order Taylor series approximation correction here. So you get like, you still have a little bit of error, you still have like a second order error, but you get rid of the first order error. And the idea is what is the dual of the program? The dual of the program is the value of a treated unit or the value of a control unit, depending on which control constraint you're using. And the technique works amazing. So for this one, I did for the simulations here. So the technique works amazing because this is we did this like ride share experiment, like a whole day worth of data. And if you don't correct, let's say you have an effect size of 10%. If you don't correct, if you have very little requests, you don't have a lot of interference, you're fine. Now, if you're in a very dense marketplace, now suddenly if you don't correct, you're pretty far off. And the diamonds here are what our method does. So this is without correction. This solid line is a true result. And the diamond that's almost at the right spot is a result of our method here. So that's it. Thank you very much.
Any questions? We can just take questions offline. We can go for lunch. We'll be back in 2.